Hey folks, Mr. Fransky here. We're going to talk about, this is 6.2. This is the dot product of vectors. So we're going to start with some bell work, stuff that we learned in the last section. So first thing I want you to do is find the components of a vector with magnitude 5 and direction 280 degrees. So I'd suggest drawing a picture of that. And then vector v starts at 4, 7 and ends at negative 2, 1. Find that magnitude and direction. So if you want to pause the video and try the bell work, feel free, and then we'll do it together. All right, so the first one, remember that any vector v, the components of it can be gotten by magnitude of v times cosine theta, and then magnitude of v times sine theta. So we're just going to do that and use our calculator. So magnitude 5, direction 280. V is going to be 5 cosine 280, and then 5 sine 280. Got my calculator here. So if I do 5 cosine of 280, I get am I in degree mode? Yep. I am. So it's 0.868. And I'll show you why that is. That actually makes sense. And then 5 sine of 280 should be pretty close to 5. Negative 4.92. So let's think about where this is. I should follow my own directions and draw a picture first. So magnitude of 5, direction of 280. 280 is just past 270, so it's going to be right about here. Okay, magnitude of 5. So just barely past that mark. So that makes sense that the x-coordinate is really small, and the y-coordinate is negative and really close to 5. Okay, so we got our components of that vector right there. Not too bad, just use the formula. Now for this guy, we got v starting at 4, 7 and ending at negative 2, 1. For this one, I'm definitely going to want to draw a picture. Something like this. 1, 2, 3, 4. Let's say this is 7. So right here, we're at 4, 7. And then it ends at negative 2, 1. It's right there. So the vector looks like that. And so that looks like an x change of negative 6. And the y change goes from 7 to 1, so that is also negative 6. That's not too bad. Then with the magnitude and direction. So if I draw this in standard position, is it really negative 6 and negative 6? We'll double check. Yep, looks like it. So negative 6 and negative 6 is in the third quadrant right there. Negative 6 and negative 6. Now the direction on this one shouldn't be too bad because I know that this is 45 degrees. So 180 plus 45, my direction theta is going to be 225 degrees. And then the magnitudes, the magnitude of vector v is going to be the square root of 36 plus 36, which is the square root of 72. You can pull a 36 out of that. That is 6 root 2. So either one of those is fine. Remember, I don't really care if you can rationalize that at this point. All right, so let's see what we're going to learn today. So we've added vectors. The question is, can we multiply them? Can we multiply vectors? So there are two ways that are kind of accepted as multiplying vectors. One is by using what's called the dot product. If you take a vector v and you dot it with a vector w, this is called the dot product. And that's what we're going to mostly focus on today. The dot product takes two vectors and it turns them into a number or a scalar. There's another one called the cross product. Cross product, very clever names here, right? Dot and cross. The cross product. And the cross product is one that's very useful in three-dimensional vectors, and there are some applications in 2 dimensions as well, but for the most part, we are not going to look at that one. So we're just going to look at the dot product, and the dot product is what we're going to focus on today for our lesson. So it's kind of like a multiplication, but you really can't multiply two vectors. So we're going to take a look at what this whole dot product is. So the dot product, this is also called the inner product. The cross product is called the outer product. So the inner product or the dot product is pretty simple. If we have two vectors, w, which has components w1, w2, and vector v, which has components v1 and v2, then v dot w is equal to, sorry, that should not be a vector. I'll make sure, whoops, too far. Pen, give me a color, blue. There we go. So v dot w, what you do is you multiply v1 and w1, and you add to it v2 times w2. Now, remember, these are two vectors that we're dotting. And what do we end up with? Well, if you multiply the first components and we add to it the multiplication of the second components, this is a number. Or the fancy word for a number we've been using with vectors is a scalar. So often you talk about like mapping. You say you're taking two vectors and we're sending them to a number. Okay, so we're taking two vectors and we're sending them to a number, and this number is going to have some important applications. But for now, we really just want to focus on this formula. Okay, so if you write down one formula today, it's this one. There's another pretty important one we're going to get to in a second, but this is definitely the formula we want to write down. So v dot w is the first components multiplied plus the second components multiplied. So let's do a really simple example of this. So if we have, let's do 3, 4 dotted with 5, 2. So we just follow the formula. 3 times 5 is 15, plus 4 times 2 is 8. That is 23. So every time you have a dot product, you are going to end up with a number. That is very important. So dot product leaves you with a number, or a scalar. Okay, so a scalar, remember, is just a number. It's not a vector. So every time I see a dot product, I should not see you have an answer as a vector. It should be a number. Make sure that's a number when you get it. Okay, let's take a look at another example. If v is negative 2, 8 and u is 4, negative 3, find u dot v. Give this a shot if you want to. You can pause the video and try it if you want to on your own. All right, let's see what you got. So u dot v, what I'm going to do is I'm going to multiply the first components, which is negative 8, and I'm going to add to it the multiplication of the second components, which is negative 24. It's going to give us a negative number. That's going to be negative 32. Okay, so once again, we took a dot product, ended up with a number. That's very important. Okay, so let's talk about some of the properties of the dot product. Some of them are intuitive. Some of them I think require a little bit of thinking. Because like, if you think about like properties of, I don't know, multiplication. Right, so some of the properties of multiplication, a times b is the same as b times a. Now with things like the dot product, we're introducing a new idea of how to combine two things, right? We never combined two vectors like this before. So it's worth thinking about. Can you do that? Is dot product commutative? And that's actually the first thing, is that they are. Because think about it, if you mixed up the u and the v, all that would happen is you'd have v1 times u1 and v2 times u2. So when we're adding it together, it's going to be the same thing. So that's our first property. Our first property of vectors is dot product is that u dot v is the same thing as v dot u. And again, it might seem simple, but this is different than just regular multiplication, so we have to think about these things. The second thing is that we can use the distributive property. So u dot v plus w is equal to u dot v plus u dot w. Now, if you want to, you can do this with components. If you have u is a, b, or something, or maybe u1, u2, v is v1, v2, and w is w1, w2, you can convince yourself. If you add these together and then you dot the u in, you'll end up with u1, v1 plus u1, w1 plus v1. You end up with everything that you need in order to make the two dot products summed together. All right, the third one is pretty trivial. With 0 with a line on top of it, this means the 0 vector. That means 0, comma 0. So if you dot 0, 0 with any vector u, think about what would happen. No matter what the components of u are, when you multiply each one by 0, it's going to turn it into 0. So 0 dot u is always the 0 vector, because it's going to give you two zeros again. So no matter what u has for components, when you multiply them each by 0, you'll end up with the 0 vector overall. The next one is that if you take a scalar, this is number 4, so if you have a scalar, let's say c, then if you have cu, so if you scale u by the scalar c, and then you dot it with v, this is another one that's not too hard to prove if you want to try it on your own, but you can put that c value wherever you want. That is the same as u dot cv, or you can also do c times u dot v. So this is just saying you can scale with u, or you can scale with v, or you can dot first and then scale. No matter what you do, every time you're going to end up with the same number. Remember, each one of these involves a dot product, so it's going to end up giving you a number overall. Now, I save this one for last because I kind of want to prove it a little bit. And this is a proof that you guys would be able to do just fine. Let's think about what happened if you dot a vector with itself. U dot u. Well, let's think about that. Let's say that u is u1, u2, like we have up here. Actually, let's do it a little bit differently. Let's do u is ab. Okay, u is ab. So if you do u dot u, that would be a times a plus b times b. That is a squared plus b squared. Interesting. That sounds very close to a formula that we've used a lot in the last few days. Remember how the magnitude of u is the square root of a squared plus b squared? So what is a squared plus b squared on its own? How can I get rid of this square root? Well, you can square both sides. So if you do u dot u, what you end up with is the magnitude of u squared, because magnitude of u squared would be a squared plus b squared. So if you dot a vector with itself, that's kind of interesting. You end up with the magnitude of the vector squared, and we're going to use that in the next example. So these 5 properties are ones that you should be familiar with, and a lot of them, like I said, are intuitive, right? It seems like it makes sense that they're commutative. It also seems like it makes sense that you can use the distributive property. If you dot 0 vector with any vector, you get 0. If you have a scalar c, you can put it wherever the heck you want. But this last one is kind of interesting. If you dot a vector with itself, you end up with the square of the vector's magnitude. Let's try an example with that one. Use the dot product to find the magnitude of this vector. Well, we were just told that if we dot u with itself, we'll end up with the magnitude of u squared. So I'll do the dot product, and then I'll just take the square root. So the dot product would be 4 times 4 plus negative 3 times negative 3. That is 16 plus 9, which is 25. So then, we know that is the magnitude squared. That's one of our properties. So if I want the magnitude, what do? Well, I'll just take the square root. Square root of 25 is 5. So we found the dot product, which really is a lot similar to finding the actual magnitude itself. We just didn't take the square root. And then we took the square root, and we ended up with 5. So if you're told to use the dot product to find the magnitude, show me you're finding the dot product. And then after you're done with that, take the square root. That's all there is to it. Cool. Now, finding the angle between 2 vectors. What's going on here is we're saying, okay, we've got 2 vectors. Vector, I want to make sure I do this the same way I did. Let's say this is vector v, and this over here is vector w. Okay? Different magnitudes, different directions, and I'm interested in finding the angle in between them right here, theta. Now, I'm going to go through a process here that you don't need to know. So I drew my proof hat here so that you knew that, this is something you don't need to know how to do. But once we get the formula for the angle, that is a formula you're going to want to write down. So if I'm interested in this angle right here, what I need to do is, look at this. If I draw in a triangle, a third part of the triangle here, maybe I'll use a different color for that, maybe red. If I could find the length of this triangle, and I know the length of v and the length of w, I have a side-side-side triangle. If you remember, if we're looking for an angle of a side-side-side triangle, we can use the law of cosines to do that. So the first thing we need is we need to figure out, can we find that length? Well, this almost looks like what we did with vector addition. Remember when we did that? We said if you start at 0, 0, you take one vector, and then you add another vector to it in another direction, tip to tail, that the resultant vector, let's go back to blue, is going to be the sum of those 2 vectors, this guy right here, right? So that would be the sum of the 2 red vectors. This case, though, we don't have them tip to tail, but I think we could get them tip to tail. How could I flip one of these vectors over? Any ideas? Well, think about it this way. If you have a vector here that is, let's say this is 2, 3. Should put pointies on there. There we go. Okay. So let's say this is at 2, 3. How could I get one going exactly the opposite direction? You have any ideas? What if we made both of them negative? What if we did -2, -3? I think that would go exactly the opposite direction. And it would have the same magnitudes. This would be -2, -3. So we could do that with v. Let's do that. So if we flip it over, it'll have the same magnitude. So this is now negative vector v. All we're doing is really scaling it by -1. This is still vector w. And now we have tip to tail. So what is that red vector? Well, that red vector would be the sum of -v and w. So -v plus w, or how can we write that a little bit nicer? Looks like w minus v. So now we're looking for this angle theta down here. Go back to blue. What we can do is we can use law of cosines with the magnitude of all 3 of these vectors. So I'm going to kind of write the first line here, then I'll go to a new page so we have a little bit more room to work. So remember, with law of cosines is c squared equals a squared plus b squared minus 2ab cosine of angle c. The side you use has to be across from the angle you want to find. So we're going to have to use this, the magnitude of w minus v as our c. So we're going to do magnitude of vector w minus vector v squared is equal to the magnitude of w squared. Now for v, we could say the magnitude of negative v, but would you agree with me that that magnitude would be the same as positive v? Because really it's going just in the opposite direction, but magnitude is always positive. So I'm just going to do this plus the magnitude of v squared, and then minus 2 magnitude of w, magnitude of v, cosine of theta, where theta is the angle in between the two vectors. Okay? So now, I'm going to take this idea and we're going to start doing a little bit of algebra with it. I might actually be able to fit it here. Nah, I don't think I want to do that. But, well, let's see. Let's see if I can do it, because I don't really want to write this again. So magnitude of w minus v squared. Let's think about what that's going to be. Using one of our properties, we said that if you dot a vector with itself, it gives you the magnitude squared. So if you dot a vector with itself, it gives you the magnitude squared. Well, we're going to kind of go the other way now. So we have the magnitude of this vector squared. We know then that is w minus v dot w minus v. And now what we're going to do is we're going to use, so we're just going to work on this left side a little bit. Then maybe I'll go to a new page once we have the left side worked out. So we just use the property that the magnitude of a vector squared is equal to the vector dotted with itself. So we have w minus v dot w minus v. So what we're going to do now is use our fact that we can distribute to just FOIL this out a little bit. So w dot w minus w dot v minus w dot v again. It's really v dot w, but because it's commutative, we can write it as w dot v again. Okay? And then it looks like plus v dot v. Because it'd be negative v dot negative v, but that's going to end up being two negatives, which make a positive. So let's see what we have here. W dot w, that is magnitude of w squared. Then we have minus w dot v twice. So we have minus 2 w dot v. And then we have plus v dot v, which is magnitude of v squared. So we keep using this property that if you dot a vector with itself, it makes the magnitude squared. And that is equal to magnitude of w squared plus magnitude of v squared minus 2 magnitude of w, magnitude of v, cosine of theta. Now check it out. So this goes away. Magnitude w squared goes away. Magnitude of v squared goes away. So let's take what we've got and go to the other side. So one thing more is going to cancel, it looks like. Let's go to the next slide, though. So at that point, we had negative 2, was it w dot v? Yep. So negative 2 w dot v is equal to negative 2 magnitude of w, magnitude of v, cosine of theta, where theta is the angle in between w and v. Okay. So now we can divide by negative 2, and we end up with our next very important formula of the day. W dot v is equal to magnitude of w, magnitude of v, cosine of the angle in between them. This is a very important formula. So at this point, basically what we have is two ways to get w dot v. So w dot v could be w1 v1 plus w2 v2, or we can calculate it in this other way, which is magnitude of w, magnitude of v, cosine theta. So there are two different ways to calculate this. Now, this is one place in physics that use the dot product a lot. If you knew the magnitude of two forces, the magnitude of two forces, you can find the angle in between the two forces by using the dot product. Or you can find the dot product by using the right side. Either way you go. What we're often interested in math is finding the angle in between the vectors. So sometimes this formula you actually want to solve for theta. So we divide by magnitude of w and magnitude of v. So we have cosine theta is equal to w dot v divided by magnitude of w, magnitude of v. And then if we want to find theta, we would just take cosine inverse. So cosine inverse of w dot v divided by magnitude of w, magnitude of v. We're going to try some examples with that. Okay? Let's take a look. So make sure you have these two formulas written down. They're really important. So we're going to find the angle between some of these vectors. So first we're going to find the angle between u and v, which are 2, 3, and negative 2, 5. And we're going to use this idea that u dot v is magnitude of u, magnitude of v, cosine theta. I changed from w to u, but same formula. So what we're going to do is we're going to put in everything that we know. Well, we can find u dot v, right? U dot v we just get by multiplying components. So 2 times negative 2 is negative 4, plus 3 times 5, which is 15. That's the left side. That's our dot product. So we found that using our other formula. Is equal to the magnitude of u. Well, the magnitude of u is the square root of, looks like 4 plus 9. That's 13. So root 13. So root 13 times magnitude of v, which is the square root of 4 plus 25, which is root 29. So root 13 times root 29 times the cosine of theta. All I'm missing is theta. I knew how to find the dot product because I would just use the inner product, the 2 times negative 2 plus 3 times 5. And then I knew the magnitudes by using square root of a squared plus b squared. All I'm missing is theta. So let's solve for theta. So I might start doing some work with the calculator now. Negative 4 plus 15 is 11. So 11 is root 13, root 29, cosine theta. Now maybe I'll take my 11 and divide by root 13 and root 29. So 11 divided by root 13, I'm working with my calculator here, gives me 3.05. Now I'm going to divide by root 29. So that gives me 0.566 is equal to cosine theta. Good. That should be a number less than 1 for this to work. So theta is going to be cosine inverse of 0.566. So I'm going to do second cosine of that answer. That gives me 55.49 degrees. Cool. So we found the angle in between u and v. Now maybe you want to try this one on your own. Try to find that same pattern, and then we'll come back and we'll try it together. All right, let's give it a shot. So once again, we're going to find the dot product on the left side. So 2 times negative 1 is negative 2. And then 1 times negative 3 is negative 3. That's going to be equal to the magnitude of u. Magnitude of u is going to be the square root of 4 plus 1. That's root 5. Times magnitude of v is going to be the square root of 1 plus 9. That's root 10. Times the cosine of the angle in between them, theta. Negative 2 minus 3 is negative 5. We're going to divide by root 5 and divide by root 10. And that'll be our cosine theta. Let's calculate that. So do negative 5 divided by root 5. And then take that and divide by root 10. And I get negative 0.7071 is cosine theta. So then we do cosine inverse of negative 0.7071. And we get 135 degrees exactly. Cool. So that's actually one of the nice unit circle values. So you might have recognized this as root 2 over 2. 135 degrees. Pretty neat. All right, one more thing I want to say. So if we use this idea that v dot w is equal to magnitude of v, magnitude of w, cosine theta, we want to think about when are vectors perpendicular. Well, perpendicular means that they intersect at a 90-degree angle. Okay, so you have your vector v and your vector w. So the angle between them, theta, is 90 degrees. Let's think about this. Cosine of 90, what is the x-coordinate at the top of the circle? It's 0. So if you have perpendicular vectors, that means that this piece is 0, multiplied by the magnitudes, doesn't matter what they are, is going to make 0. So what does that mean? That means that v dot w is equal to 0. Interesting. So this is actually an if and only if. And we're going to introduce a fancy word. Perpendicular vectors, this is a definition. Perpendicular vectors are called orthogonal. Some people say orthogonal. It's the same word. Orthogonal. So ortho means 90 degrees. They intersect at a right angle. You see that a lot. Orthoscopic. There are joints in your body that they use orth as a prefix because it means they intersect at a 90-degree angle. And so orthogonal just means that two vectors are perpendicular. So this is an if and only if. So vectors, so two vectors are perpendicular, or sorry, orthogonal. I'll use our fancy word. Why not? So two vectors are orthogonal, or orthogonal, if and only if. It's an if and only if. It's a biconditional. if and only if v dot w is equal to 0. Okay, so if the dot product is 0, it guarantees that those vectors are perpendicular. So our last example we're going to do today is to prove that two vectors are orthogonal. Oh, I used an O there. I'm pretty sure it's an A. Pretty sure it's orthogonal with an A. Well, you can look it up if you want to. Like I said, I can't spell. So we're going to check the dot product. That's all we're going to do. We're going to do 2, 3, dotted with -6, 4. So if we do this, we're not going to do the dot product the hard way. We're not going to do it where we find the magnitude and do all that. We're going to do it the easy way. 2 times -6 is -12. 3 times 4 is +12. -12 and 12, 0. Therefore, vectors are orthogonal. Now I'm starting to second guess myself. I think it might be an O. I don't know. It doesn't matter. Anyway, so the point here is if you dot product two vectors, do it the easier way of the two. Sometimes you're given certain information and you can find it one way or the other. But if you're given just the components of the vectors, for sure just do 2 times -6, 3 times 4, add them together, you get 0, guarantees that those vectors are perpendicular or orthogonal. Pretty cool. That's all I've got for you today, guys. Take a look at the homework, and I will see you guys when I am back. Love you guys. That's why I'm here. Have a great day.